Hello everyone, welcome to this London machine learning meetup. So my name is Anna and I'm going to quickly introduce you to what to expect tonight, introduce the first speaker and then hand over the stage to him. The logistics, first of all, thanks for MAN AHL for sponsoring this again. They will have a short announcement later on. Otherwise, there will be the first talk for 45 minutes roughly, then questions, some time for community announcements and a bit more networking, and then at the second talk. Yes, the first speaker is Ryu. He'll be presenting on what is part of his PhD, neural networks and decision trees. He's currently a PhD student at UCL on a Microsoft Research Scholarship. And yes, I think so. We'll see something on neural networks, decision trees, and applications to medical.
So there's not going to be medical imaging.
No applications at all.
Yeah.
Okay, no applications at all. Cool.
All right, thank you very much, Anna. Hi, everyone. I'm Ryu. I'm a final year PhD student at University College London. And today, as the title says, I'm going to be talking about neural networks and decision trees and how to combine the two. So neural networks and decision trees are both powerful classes of machine learning algorithms with proven successes in academic and commercial applications. However, typically the two approaches come with mutually exclusive benefits and limitations. And in this presentation, I'd like to talk about our recent attempt at combining deep neural networks and decision trees in such a way that enjoys the benefits of the two approaches while trying to minimize their limitations. So before getting into the core of the talk, I'd like to set the context by illustrating the key difference between the deep neural networks and decision trees. So typically, deep neural networks are characterized by learning hierarchical representation or features of data. In supervised learning setting, neural networks learn a complex nonlinear transformation to apply to input data, so a simple linear model can adequately perform the task of interest, such as classification or regression. A commonly used example is the range of features learned at different layers in a CNN trained for classification tasks, learning oriented edges and colors at the bottom and the textures in the middle and object parts at the top. On the other hand, decision trees are characterized by hierarchical clustering of data. A decision tree learns how to split the input space in a hierarchical fashion, so in each subset, a simple model such as linear model can explain the data well. So here's an example from my previous work where I trained a decision tree for super resolution of brain MRI images. So in this case, I assigned a color to each subset of the partitioned input space so that we can understand the internal decision-making process within the tree hierarchy. And you can see that at the first split, the brain tissues and water are separated. And at the next level, white matter and gray matter, which are two different categories of brain tissues, are subsequently split. And as you go deeper down the tree, even finer partitions are carried out until you eventually get these sort of final forms of partitions, which has some interesting resemblance to the actual brain structures. So these two approaches have their pros and cons. So a key advantage of neural nets is its ability to learn features and representation of data. This means that unlike many other machine learning algorithms, humans do not need to design good features for the algorithm to do well. Another key advantage is scalable training with stochastic optimization, such as stochastic gradient descent. Consequently, with modern compute power that we have access to, we can train a very large network on an extremely large data set, and this allows neural networks to attain very good performance in many, many tasks where you have large amount of data, such as language translation, speech recognition to image understanding. However, architectures of neural networks typically need to be designed by humans, and specifying a model at the right level of complexity could be a burden on practitioners and requires domain expertise. Also, inference can be heavyweight for a very large model, as each input data engages every part of the model. In other words, if you want to increase the capacity of the model, you need to proportionally increase the computation. On the other hand, the architectures of decision trees are optimized based on training data, or trees are growing in a data-driven fashion. And they display advantages, particularly in data-scarce scenarios. Also, decision trees often enjoy lightweight inference thanks to the property of what's called conditional computation. What I mean by that is, at inference time, only a single path on the tree is used for each data point, engaging a fraction of the model. However, unlike deep neural networks, decision trees often require hand-engineered features of data, which require domain knowledge. And this is partly because the expressivity of the model is limited due to the splitting functions taking the form of axis-aligned features. So axis-aligned features are effectively simple thresholding on hand-engineered features. And the cost function, there's a reason for that, and that the cost function used for optimizing the hard partitioning of data space is not differentiable, and this prevents us from using complex splitting functions in high-dimensional problems. And the present solution to this issue of limited model expressivity is unsambling, often in the forms of random forests or gradient-boosted trees or XGBoost. And these ensemble methods are often used in more complicated problems, and they are known to achieve state-of-the-art performance in many tasks. And they still remain a competitive choice of algorithms for many practical challenges in Kaggle, for example, such as financial forecasting. So as I mentioned at the start, the goal of this work is to combine deep neural networks and decision trees. To design an algorithm which have the benefits of the two approaches and avoids their limitations as much as possible. And to that end, we propose adaptive neural trees, or ANTS in short. Here, I'd like to note that there's a large body of existing research in the past that attempted the same unification. And I suppose the main contribution of ANTS is to provide a simple yet general framework through which to think about the limitations of such previous works and design ultimately something better. In particular, we'd like to demonstrate that ANTS enjoy the following complementary benefits of the two approaches, namely feature learning and scalable optimization via stochastic gradient descent from the world of deep neural networks, and architecture learning and conditional computation property of decision trees. We formulate ANTS for supervised learning tasks and illustrate these properties on regression and image classification tasks. ANTS are comprised of two key features. So firstly, we propose a novel form of decision trees which use neural networks in both its edges and nodes of the tree, combining abilities of representation learning with hierarchical data partitioning of the tree. Secondly, we propose a backpropagation-based training algorithm which grows the architecture in a progressive fashion from simple building blocks. And I'm now going to describe each of these aspects in more detail. So an ANT, what is an ANT? So an ANT is defined as a form of binary trees with a set of neural network operations defined on it. And here's an example of a binary tree. Every node is a child of exactly one parent except the root node at the top, which has no parent. The nodes with no children at the end of the tree are called leaf nodes, and they're shown as gray circles. And the remaining white circles are called internal nodes. And each of internal nodes has exactly two children. Looks like it doesn't shut the cursor. So every node and edge in the binary tree is assigned with an operation. And in particular, we consider the following three types of operations denoted by R, T, and S, which stand for routers, transformers, and solvers. So every internal node has a router module, which is a binary classifier which sends the allocated samples either to the left or the right child, with probability given by the function R. And edge of the tree has one or composition of multiple so-called transformer modules. So each transformer is a nonlinear function that transforms the incoming samples and passes them to the next operation. So this can be, for example, a combination of one convolution layer and ReLU nonlinearity. And lastly, each leaf node, shown as gray circles at the end of the trees, are called assigned with solver modules. And each solver module takes the allocated samples and performs a task of interest, such as classification and regression. Just to give you an example, the red shaded path shows the routing of this cat image to reach leaf node 4, where the class probabilities are generated at the end. And as the input X traverses the path, it undergoes a sequence of nonlinear transformations on the edges on the way, T0, T1, and T4. And when it eventually reaches leaf node 4, the class probabilities over dog or cat class are given. And the probability of taking this particular path is given by the product of the respective routing probabilities. Right. And each ANT effectively models the class distribution over the given input image as a type of what's called hierarchical mixture of experts, which was originally proposed by Michael Jordan in 1994. In this case, the routing is probabilistic. So there's non-zero probability of the input X to reach other leaf nodes, such as leaf node 2 and leaf node 3. And the full predictive distribution is given as the average of all the leaf node predictions weighted by the respective probabilities of reaching them. The key difference with a traditional hierarchical mixture of experts is that the input image is transformed, not only routed, but also transformed. And at test time, we consider two inference schemes, so namely multipath inference and single path inference. So multipath inference uses all the leaf nodes, uses the entire predictive distribution defined above, engaging all the leaf nodes on the tree. But this can be expensive for a deep and wide tree. So we therefore also consider a lighter weight version or approximation of multipath inference called single path inference, which is quite simple. We just, in some way, we basically pick a single leaf node and use the prediction from that chosen leaf node as the final estimate. And the way we choose that leaf node is by greedy traversal. So we greedily traverses the tree in the sort of directions of the highest confidence of routers. So if at one point, if routing function outputs probability above 50%, you always send it to the right and otherwise to the left, and you sort of repeatedly use the same logic to traverse down the tree until you hit one of the leaf nodes and you use that prediction from that corresponding leaf node. And this way, the single path inference constrains the computation to a single path and allowing for more memory and a time-efficient inference. Right. So now I'm going to describe how each ANT is grown and optimized. So training of an ANT proceeds in two phases, namely growth phase and fine-tuning phase. The growth phase progressively grows the architecture of the model based on local optimization, while the refinement phase fine-tunes the parameters of the grown model based on global optimization. For both phases, we use negative log likelihood as the common objective. In this case, we assume that all the component modules, routers, transformers, and solvers are differentiable, so we can use standard gradient-based optimization. So as is typically the case with neural networks, we use backpropagation for gradient computation and use gradient descent to minimize the loss. The second phase is quite simple. So the refinement phase takes the ANT, the discovered architecture of ANT, and learn from the growth phase, and fine-tunes the parameters of all the component modules by minimizing the loss function. But now, how does the growth phase work? Growth phase repeatedly applies the following sequence of 3 steps until some termination criteria are met. So starting from the root node, we choose one of the leaf nodes in breadth-first order, and we construct 2 new models, namely split and deepen. First model, split, extends the current model by splitting the node by adding a router. And the second model, deepen, it increases the depth of the edge by adding a new transformer. And step 2 optimizes locally the parameters of the newly added modules while fixing the parameters of the remaining part of the graph. And step 3 executes the option with lowest validation loss. And if the loss is reduced by neither extensions, we keep the original node as it is. And the rationale behind, and this process is repeated to all new nodes level by level until normal splits or deepen past the validation test. The rationale behind this scheme is to give the model a freedom to choose the best option between going deeper or splitting the data space. And it's also worth noting that local optimization is both space and time efficient. This is because gradient computations are constrained to the new peripheral part of the tree, and thus forward activations do not need to be stored in memory. And this is going to be the last slide before moving on to the experiments and results. So as I mentioned at the start, there's a large body of previous work which attempted combining the decision trees and neural networks. And here I'm going to give a quick survey of such works and explain how ANTS provide a simple generalization and elucidate their limitations. The table on the slide shows different sort of aspects of ANTS, or aspects of what I think are important for when combining the two approaches. The first column denotes if the routers learn features from data, and the second column indicates if each path on the tree is a neural network. And the last column on the right indicates if the method grows an architecture or uses a pre-specified one. So the very first soft decision tree proposed in 1999 by Suarez is a specific case where, in our terminology, the routers are simple thresholding on hand-engineered features, or also known as axis-aligned features. And the transformers used in this case were identity functions, and the routers are simple static distributions over classes. More modern forms of decision trees used linear classifier, multi-layer perceptrons, or convolution layer in the routers in order to learn more complex partitioning of the input space. However, they still relied on simple identity transformers, which meant that each path on the tree does not perform any representation learning, and this constrained their predicted performance. Previous work has also suggested that integrating nonlinear transformations into trees enhanced the predicted performance of the models. The notable, I think notably, the neural decision forest proposed in 2015, which in fact held the state-of-the-art performance on ImageNet in 2015, is an ensemble of decision trees, each of which is also an instance of ANTS, where the whole GoogleNet architecture is used as the transformer at the root node prior to learning tree-structured classifiers based on linear routers. And another notable example is the conditional network proposed by Yanni in 2016. So they specified existing convolutional neural network architectures by distributing computations on hierarchical structures. And I think they used MLP-based routers. And they managed to show that they can reduce compute cost and number of parameters without actually compromising the performance at all, or accuracy. But however, in both of these cases, the model architectures were pre-specified and fixed. So in contrast, adaptive neural trees provide a simple general framework for learning a tree-structured model with a capacity of representation learning along each path and routing decisions, and of optimizing its architecture. So now I'd like to evaluate the performance of ANTS on regression and classification benchmarks. So first dataset is called SARCOS dataset, and it's a multivariate regression dataset where the task is what's called inverse dynamics problem, where you want to predict the torques of a robotic arm from its position, velocity, and acceleration. And MNIST is a very well-known classification benchmark consisting of handwritten digits from 0 to 9, and is used for sanity check. And the Cypher 10 is an object recognition dataset which consists of natural images of different kinds of animals and vehicles. And a task is the same as immunist. You want to classify each image into one of the 10 classes. And using these datasets, we want to perform the following experiments. So first, we compare the performance of ANTS to relevant decision tree and neural network models. Secondly, we illustrate the ability of ANTS to learn meaningful hierarchical structures in data. Thirdly, we examine how our proposed growth procedure adapts the model complexity to varying amounts of training data. And lastly, we look into the effects of global refinement phase on ANTS and show that it can automatically prune the trees. Right. So for all of these experiments, we trained variants of ANTS with different choices of building blocks, routers, solvers, and transformers. And routers, solvers, and transformers are defined based on 3 types of very standard neural network operations: convolution layer, global average pooling, and fluid connected layer. And the solvers are always defined as linear models, while routers are binary classifiers with a sigmoid output. And for the training of all ANTS, we used mini-batch Adam optimizer. Right. So we have run lots of experiments and compared against different baselines on 3 datasets. But for now, I'm going to skip this slide and first show different nice properties of ANTS. And later, I'm going to come back to this and dissect these numerical results, focusing on particularly important bits. And also the details are in the paper. So first, I'd like to illustrate the ability of ANTS to discover meaningful hierarchical structures in data, which is useful to the end task, in this case, classification. Learned hierarchies often show strong specializations to certain classes or categories of data on both MNIST and Cypher-10 datasets. And here's a cherry-picked example of a learned ANT architecture with particularly human interpretable structures. So here I'm feeding a bunch of example Cypher-10 images into ANT, which are categorized into 2 groups by the first router. Can you sort of guess what kind of sorting might be happening here? So these bunch of images are categorized into man-made and natural objects by the first router. And the group of man-made objects on the left is subsequently categorized into road vehicles, such as cars and trucks, and non-road vehicles, such as planes and ships. And these are the corresponding histograms. The histograms in red visualize the distribution of test examples allocated to respective branches, and the histograms in blue show the distribution of routers' decision probabilities. You can see that decision probabilities of routers are quite concentrated around 0 and 1, and that means this sort of hierarchical categorization was carried out with high confidence. And what I would like to highlight here is that human intuitions on relevant hierarchical structures do not necessarily equate to optimal clustering of data. I think rather I would like to emphasize that these hierarchies are automatically learned to optimize the end task performance. And this is possible and only visible to the users thanks to the freedom of ANTS to learn when to separate and share representations. We also observed that most learned ANTS are unbalanced. This means that different categories of data undergo different amounts of computation or processing. This property of adaptive computation is plausible since certain types of images may be easier to classify than others. So next, we assessed the property of adaptive model complexity. So one strength of ANTS is its ability to adapt the model structure to the given availability or complexity of the training dataset. On the other hand, oversized models without regularization are vulnerable to overfitting on small datasets, and undersized models would, of course, lead to underfitting. So in this experiment, we trained 3 variants of ANTS on subsets of Cypher-10 of varying size starting from only 50 examples all the way to 45,000 examples. And also for comparison, we trained all convolutional neural network, showing us the blue line, and linear classifier, the gray line on the plots, on different subsets of cipher 10. And yeah, what was I going to say? So figure on the left shows the corresponding test performance of respective models as a function of the dataset size. And the figure on the right plots the total number of parameters as a surrogate measure of model complexity. So we see that all of the variants of ANTS, orange, green, and red, achieve comparable or better performance than the baseline all convolutional CNN, blue one, consistently, and in particular, the smaller the training set gets, the larger the improvement we observe, where the difference can get up to 13%. Figure on the right shows that the model size of ANTS generally increases as a function of the training dataset size. On the other hand, baseline or convolutional neural network has a fixed number of parameters. So please see the figure. So on the figure on the right, so all convolutional neural network has a fixed number of parameters consistently larger than any of the learned ANTS, and suffers from overfitting, particularly on small data sets. And the linear classifier, on the other hand, underfits the data with consistently poor training and validation performance. So these results support the ability of potential of ANTS to construct models of adequate complexity, embodying Occam's razor, and leading to potentially better generalization. And we also looked into the effect of global refinement. And so global refinement phase, just as a reminder, is basically the second step of the training where the parameters of the discovered ANT model is fine-tuned. And this figure plots the test accuracy as a function of epochs, where the dotted lines show the epoch at which the model entered the refinement phase. And you can see that while all three models initially undergo a steep drop in accuracy, they eventually all converge to higher test accuracy. And this is presumably because the global optimization potentially remedies suboptimal decision made during the growth phase due to local optimization. And in order to test this hypothesis, we compare the dynamics of ANTS before and after the refinement phase. So this is before the refinement, before fine-tuning. In many cases, we observed that global refinement, global optimization polarizes the decision probabilities of routers, which lead to pruning of some branches. In this example, you can see that the decision probability of routers, shown as the histograms in blue, are more concentrated around 0 or 1 after the fine-tuning. So this is before the fine-tuning and after the fine-tuning. And as a result, one of the branches is pruned. So in essence, the probability of selecting that pruned node has effectively become 0. And the resultant model attains better generalization error, displaying resolvement of suboptimal partitioning of data. So now, I will talk about the quantitative results on 3 datasets, which I skipped past earlier. So I'm going to start with the SARCOS dataset, where the task is to predict 7-dimensional talks from 21-dimensional inputs, which consist of like 7 positions, velocities, and accelerations. And in this bar chart, the blue bars are showing the predictive errors, or mean squared errors, for multipath inference, while the green ones show the corresponding results from the single path inference. So earlier, I introduced 2 different inference schemes, multipath and single path inference. So multipath is the one that engages every single leaf node on the tree. It's more accurate, but more expensive, while single path inference is an approximation of multipath inference based on a dominant leaf node, which is more lightweight, but potentially less accurate. So firstly, on SARCOS dataset, all the top 3 models are tree-based, with neural decision tree, gradient boosted trees, and ANT achieving the lowest mean squared error. And the set of bar charts on the right shows the corresponding number of parameters on logarithmic scale. And this red dotted line shows the number of parameters of ANT for single path inference. ANT requires less than a half of what's required for the best standard neural network models with 3 hidden layers. On the other hand, gradient boosted trees only need a magnitude less parameters. But we should also note that the total number of parameters for standard tree-based models, such as gradient boosted trees and random forests, are in fact significantly larger than that of an ANT. So all in all, ANT achieves the best accuracy on SARCOS dataset, beating both standard neural networks and tree-based methods. And secondly, in terms of computational efficiency, ANT is somewhere between neural networks and gradient boosted trees. And this highlights the value of hierarchical clustering of the input space for both predictive accuracy and speed. So we did a similar comparison on Cypher 10, object recognition dataset. Firstly, ANTs far outperform recent decision tree methods by a large margin, achieving over 90% accuracy, while the best reported variant of random forest suffers from larger than 25% classification error rate. And this demonstrates the benefit of incorporating representation learning into tree-structured models. Secondly, ANTs show competitive performance with respect to relatively recent convolutional neural network models, such as max-out, network-in-network, and all convolutional CNN, so all convolutional neural network, all of which held the state-of-the-art performance at the time of their publications in respective years. In particular, as shown by the red dotted line, ANT-A achieves the lowest classification error rate of 6.5%. Also, ANT-A requires fewer parameters during single path inference than these CNN classifiers, showing improved efficiency. Here, I'd also like to note that these CNN models have linear structures with up to 15 layers and consisting of similar set of operations to the components of ANT modules, such as convolutions, global average pooling, and fully connected layers. Oh, thanks. So, however, shortcut connections such as residual learning and dense connections achieve even better classification accuracy. So residual network with 110 layers achieves slightly better classification accuracy than ANT-A, while densely connected network achieves much better classification accuracy of around 4% error rate. However, both of these architectures use significantly more parameters. Certainly, ANTs would benefit from these architectural advances in deep learning research, but integrating them into ANT modules remains interesting future work. So on Emily's dataset, similar results were obtained, but instead of showing another set of bar charts, I'd like to show a nice learned example architecture, which comes with many interesting properties. So ANT-MNC, which has the simplest primitive modules, achieves over 98% accuracy, and a single path inference requires only as few parameters as a linear classifier. On the other hand, a linear classifier achieves only 92% accuracy. This is a very good example that illustrates the power of combining the hierarchical feature learning and hierarchical data partitioning. So although I've actually precluded from the talk, we have actually done an ablation study where the options of having transformers or routers are disabled. And we discovered that we need both routers and transformers to actually maximize the predictive performance of ANTs. So this is kind of an indication that you need both. I mean, at least in the context of ANTs, we needed both hierarchical clustering and a feature learning to attain the best accuracy. If you're interested about that, it's also in the paper, but I can also show you the results. So lastly, we tested the benefits of conditional computation by comparing the two inference schemes, multipath and single path schemes. So So yeah, so multipath inference uses all the leaf nodes in the tree, which is more computationally expensive. On the other hand, the single path inference only uses a single dominant leaf node. So as with before, the set of bar charts on the right compares the errors for depth invariance of ANTS on all three datasets, where blue bars show the errors for multipath inference and the green ones show the error for single path. You can see that errors only marginally increase with single path inference. There's a very small difference between the two inference schemes. On the other hand, with single path inference, the number of parameters during inference significantly drops, showing that single path inference is cheaper. This shows that ANTS indeed benefits from faster inference via conditional computation without compromising accuracy very much. And this close approximation comes from the confidence splitting probabilities in the routers being close to 0 or 1. Right. So, summary. In this talk, we introduced adaptive neural trees, or ANTS in short, which is a form of decision trees which use neural networks in both its edges and nodes, combining representation learning with hierarchical data partitioning. As a result, ANTS attain two key properties. So firstly, freedom to decide when to share and separate representation, which allows ANTS to learn a model that can achieve high accuracy in classification and regression tasks with lightweight inference via conditional computation. In addition, as a byproduct, ANTS are also able to automatically learn hierarchical structures in data that's useful to the end task. Secondly, we have seen that ANTS benefit from adaptive model complexity. The training algorithm grows the architecture in a progressive fashion from simple building blocks, adapting to the size and the complexity of the training data. So future challenges. So in the current design of ANTS, we strive for simplicity, and as a result, there's a substantial room for improvement. And in the future, I would be interested in scaling up ANTS to larger, higher dimensional datasets, and I think such as ImageNet or medical imaging applications. And I think that's going to require improving the optimization method so that you can train wider and even deeper ANTS. So firstly, the current growth procedure is greedy, is based on local optimization, and are therefore suboptimal. And the suboptimality of the local decisions only gets worse as the tree gets deeper and wider. In the future, we're going to look into different ways to alleviate this problem, such as more global optimization during the growth phase, or merging of branches, or training in entangled settings, sort of inspired by already sort of existing works in decision tree research. And secondly, for large trees, global optimization could be expensive. One potential solution to that problem would be to employ a Monte Carlo approximation of the training scheme by instead stochastically traversing the tree and using grading estimators for parameter updates. So such as a good starting point might be to use rainforest or straight-through estimators, or something more recently proposed methods such as rebar or relux might be interesting to try. And another challenge is to explore the value of the learned hierarchical structures in terms of interpretability, or maybe I should say algorithmic transparency. I think that the tree-shaped hierarchy provides a new means to understand its internal decision-making process. So for instance, given an image where the ant fails to classify, you could compare against a large number of correctly predicted examples and potentially localize a point of routing failure where the ant made a wrong decision, made a wrong routing decision. On the other hand, such localization of failures is more difficult in conventional neural networks with a single fully distributed representation. In addition, such hierarchical and decomposed interpretations are complementary to existing visualization techniques. So, for example, providing saliency maps along the sort of decision trajectory of routing decisions might potentially provide a layer of interpretability into the decisions made in the raw feature space, such as images. And lastly, I think extending to other tasks such as structured prediction, segmentation, super resolution, and so on, or different learning scenarios such as continual learning and generative models would also be an interesting, I think, avenue of research to explore. And lastly, I'd like to thank the main contributors of this work. So my internship supervisor, Aditya, Microsoft Research, and Antonio, who is my supervisor at Microsoft, and Danny Alexander, who is my supervisor at UCL, and Kaya Imperial College, who was an intern at MSR at the same time, and who massively contributed to this work. And also I'd like to thank Jan, Daniel, and Sebastian and Costas for the valuable discussions I had with them. Thank you very much.
Great. So before we start with questions, this is actually being recorded, so you should know before you ask. And yes, thanks to the speaker.
Great, thanks.
If you, yes.
So essentially, I just want to return to one of your slides where you showed the number of parameters for ANT based on the dataset size, and it was actually quite low for small datasets. So and the accuracy was also quite low. So do you have the insights as to why number of parameters was quite markedly reduced? Is it because of underrepresentation of samples in the datasets? I'm not sure what the dataset was used at. Or something else?
So could you repeat your question again? So is your question, why does the model complexity decrease as the training set gets smaller?
Yeah.
Yeah. So if you have a very small training set, you don't, so for the complexity of the tasks, say you don't have enough data, and if you specify a very large model, it can overfit, right? So, it's better to sort of have a simple explanation which explains the data equally well. And it's more like an empirical observation, but that's what tends to happen with ANTS.
The VG dataset, was it NIST? Or?
It was Cypher 10. Yeah.
Thank you for your talk. I wonder if the representations learned through the hierarchies, they are somehow meaningful. So if you have a man-made object and natural objects, does the vector representation of the clusters of data, can they be interpreted in any way? Do they have any arithmetic relationship with each other? So can we use them as some sort of vector representation of the cluster down the decision tree?
So how your question is, what is your question exactly?
Are the representation learned in ANTS meaningful? Meaningful,
yeah. So I guess that's a tricky question. So I don't think it's always, it is definitely meaningful to maximize the task's performance, but it doesn't necessarily have to be human interpretable. So the one that I showed is a particularly, cherry-picked example with good human interpretable structures. But that said, I think as I mentioned on the last slide of the talk, I think the learned hierarchical structure, I think, provides a sort of extra sort of new means to kind of understand sort of the decision process within the model in a sort of decomposed fashion. So, potentially is complementary to, so fast method might be example-based approach. So you could compare against a bunch of examples, you just feed a lot of examples down the tree, and you sort of cluster the examples at different, routing functions. And when things go wrong, say your image might be misclassified, and you can compare against examples that are actually correctly classified and misclassified in the same way as your image. And that would potentially provide sort of type of information that you didn't really have access to from standard neural networks.
Hi, remarkable work and remarkable presentation, so that's both really compelling. I'm sorry, I have just an understanding question about the transformers.
Yeah.
I don't necessarily understand the nature of the transformers you picked, and I'm a bit surprised to have consecutive transformers used for one representation. I would assume just in a shiny, simple linear world that one transformer would be universal enough that you don't need to have another transformer for it. So I'm assuming it's not linear, or there's something that I'm missing. Do you have an example of what are some instances where you would need two consecutive transformers?
Yeah, thanks for the question. So maybe I didn't really explain it clearly, but I think usually I think one convolution followed by ReLU or something like that. So, but I think it would make sense to define each of these modules as something relatively simple operations rather than something overly complicated. So I think what I wanted to do was kind of like, you start with something, you start with relatively simple building blocks, and this sort of like simple, greedy growth procedure sort of puts them together in a sort of tree-like shape, and hoping that it would, it would do something. Yeah.
Hi, thanks for the talk. A clarification. So when you do the single path approximation, does your loss function remain differentiable? And when you do the global optimization, does it remain differentiable? Because one would think that based on just minimal differences in the parameter, the categorization of instances will change and your loss will take a step.
Yeah, so I think that's a very good question, actually. So, so simple answer to that question is it is indeed differentiable. Both are differentiable. And the reason is that we use soft partitioning instead of hard partitioning. So each router sends samples probabilistically to either left or right. So which makes everything sort of nice and differentiable. But during training, what I do is, yeah, so that's exactly, so that's why it's differentiable.
Okay, maybe a last question? No, we covered it all. Great. So this is the point where there can be community announcements, and first of all, it's the point where AHL presents themselves.
So hello everybody, I'm Guillaume, I'm working at ManageShell, so you might have already heard the spiel, but basically we are a quant hedge fund, we are sponsoring the event, but we're also looking to recruit technologists and researchers to develop predictive model of the financial market. So if you're interested, don't hesitate to come by to discuss during the break. Thank you.
Right. So unless there are other community announcements, I would say go have a drink, and we will reunite at, say, 8:10 here.
Thanks.